Hello friends, I welcome you in lecture number 3 on Taylor and Maclaurin series. Now we are familiar with the expansion of functions using Taylor and Maclaurin series. So using Taylor series, we can express given function fx in powers of x minus a using Taylor series. So here we are given this function which is a polynomial of third degree, and we have to expand this function in terms of x minus 2, or we have to find out Taylor series of fx at x equal to 2. So now we will first find out value of function at x equal to 2, and then we will find out value of derivatives of function at x equal to 2. So first we have written this function fx is 2x cube plus 3x square minus 8x plus 7, and we find out value of this function at x equal to 2. So we put x equal to 2 here. Therefore f of 2 equal to 2 into 2 raised to 3, that is 2 into 8 plus 3 times 2 square, which is 4, minus 8 into x, that is 2 plus 7. So this is 16 plus 12. This is minus 16 plus 7. 16 will cancel out, and we have 12 plus 7, that is 19. Value of function at x equal to 2 is 19. Now we differentiate this with respect to x. F dash x is 2 constant as it is. Derivative of x cube is 3x square plus 3 as it is. Derivative of x square is 2x. Minus 8 as it is, derivative of x is 1, plus derivative of 7 is 0, and this we can rewrite as 2 into 3, that is 6x square plus 6x minus 8, and this is first derivative at any point x, and we find out value of this first derivative at x equal to 2 by taking x equal to 2 everywhere in this right hand side. So here we will have 6 into square of 2, that is 4, plus 6 into x, that is 6 into 2 minus 8, this is 24, plus 6 into 2 12, and minus 8, this is 4 and plus 24. So we have f dash 2 equal to 28. Now we again differentiate f dash x with respect to x to obtain second derivative. F double dash x is derivative of this right hand side. 6 as it is, derivative of x square is 2x, plus 6 as it is, derivative of x is 1 minus 0. So finally we have second derivative is 12x plus 6, and value of this second derivative at x equal to 2 is equal to 12 times 2 plus 6, which is 24 plus 6, and that is 30. Then we find out third derivative, that is derivative of this right hand side, which is 12. It is constant for every value of x. Therefore at x equal to 2, third derivative is 0. So now third derivative is constant, therefore fourth derivative will be 0, and all the derivatives of order greater than or equal to 4 will be 0. So we can write in this way: nth derivative at x is 0 for n greater than or equal to 4. Derivatives starting from order 4, all the derivatives of order greater than or equal to 4 will be 0. So whenever we have polynomial function of some degree, here we have polynomial function of degree 3, therefore all the derivatives of order 4 or greater than 4 are 0. So if we have nth degree polynomial, then all the derivatives of order greater than n will be 0. So whenever we have polynomial function, we will have finite number of terms in the Taylor series of polynomial function. Now we have written the formula for Taylor series of fx at x equal to 2, and it is given by f of 2 plus first derivative at 2 times x minus 2 plus second derivative at 2 divided by 2 factorial times square of x minus 2 plus third derivative at 2 divided by 3 factorial x minus 2 raised to 3 plus fourth derivative at 2 divided by 4 factorial times x minus 2 raised to 4, and so on. So we should write as many terms up to this derivatives which we have obtained. Here we have obtained non-zero derivatives up to order 3, and we have all the derivatives greater than 4 are 0. So we have written these terms up to 4th order derivative. Now in the next step we substitute all these values. Value of function at 2 is 19, value of second derivative at 2 is 28, and so that we write first f dash 2 is 28 into this x minus 2. Second derivative at 2 is 30. So here we put this is 30 divided by 2 factorial, which is 2 into x minus 2 square, plus third derivative at x equal to 2 is 12 divided by 3 factorial, which is 6 into x minus 2 raised to 3. And then all the terms after this term will be 0. All the terms starting from 4th derivative will be 0, because all the terms will contain derivatives at point 2 of order greater than or equal to 4. So we have this finite number of terms in the Taylor series, and this is going to be 15, this is 2. So this is the Taylor series expansion of given function in terms of x minus 2. We have expressed given function which is in powers of x in powers of x minus 2. So this is very nice thing. We are given a polynomial function which is a function in powers of x, and using Taylor series we are able to express this function in powers of x minus 2. Now if you observe, in earlier lectures we have not written that Taylor series of fx is equal to whatever series we obtain. We are familiar with this. This right hand side is Taylor series of function fx at x equal to a. So we are not writing equality every time. We will write down the equality whenever this power series is convergent to fx for values of x. So equality holds whenever this power series is convergent to fx for value of x. So this is convergent to fx for some values of x, and it may not be convergent to fx for other values of x. So that is the reason why we are not writing equality whenever we obtain the Taylor series of fx. But whenever we have polynomial function, then we will have finite number of terms in its Taylor series, and this will always be equal to given function. So this, if you expand this, you will obtain this same expression which we are having on the left hand side. Therefore I have written equality in this problem. So if we expand this, if we take power x minus 2 square, x minus 2 cube, and if we simplify this, then we will obtain given function. But our answer is this one. We require representation of polynomial function in terms of x minus 2. So this is our answer. We must keep this right hand side as it is. We require this answer. This is given function fx expanded in powers of x minus 2. So here this is our answer for the given question. So for this, from this problem we will make a remark that whenever we have polynomial function, then its Taylor series is finite, or we will have finite number of non-zero terms in the Taylor series of polynomial function, and we will always write equality here. So this is all about this session. I hope you like it. Thank you.